many times you still have oxygen or nitrogen. So you can try, so if you just use this carbon and hydrogen, it does not work, you may try to get okay by adding more oxygen. Or if you from your mass spectrum, you see from your mass spectrum, you can see you must have one oxygen. Then you add one oxygen. So you just remove 16, then you do the calculation again. So then you still can apply. Okay. So that way you must be try and see. So that's molecular arm. Okay, so this table shows you the common neutral laws. So if you see the molecular ion and fragment, you have mass difference. So this table shows you this difference. So possibly one kind of neutral fragment laws. It help you to identify. So you see the difference, you just check that. See possibly you have this piece of fragment in your molecule. And another thing we want to mention is the nitrogen group. So if your molecule have odd number of nitrogen, then your molecular mass will be odd. So if molecule do not have nitrogen, the molecular mass always be even. Okay. But if your molecule have an odd number of nitrogen, your molecular mass will be odd. If your molecule have an even number of nitrogen, your molecular mass still be even. So that way, if you see a molecular mass is odd, immediately remind you this molecule have an odd number of nitrogen. So when you write formula, you write, okay, you have one nitrogen. So that's this is because if you see this the molecular, the atomic mass and the valence. So if you do the combination, you will find that it always be that rule. So like hydrogen, its mass is odd, but its valence also is odd. So hydrogen forming one bond, so two hydrogen combine and one bond plus one and even odd plus odd is even. So for all these odd number mass, you also the even number mass, you also have even number of bond, so they add up still even. So only for nitrogen. Where's nitrogen? No nitrogen here. Okay. The most important one is missing. So nitrogen, you see the mass is 14, right? But the valence is 3. So like nitrogen 14, then forming 3 bond with 3 hydrogen, so 14 plus 3 then is 17. So that's why nitrogen is unique. All others, when you bonded, is even. Okay. So that's one thing reminded you when you apply that to check if that's even or the electron, also think about nitrogen. Okay. So that. 10 carbon. So that you can combine with that rule of 13, right? Since if you have more heteroatoms, so you will see the n plus 1 from the rule 13. If you do a direct calculation, so your hypothesis is no heteroatoms, you get a number, carbon number is more. So, but from the isotope, you can say, okay, my isotope only have 11% n plus 1. However, we use the rule of 13, I calculate, I get 12 carbon. So you know this isotope is direct evidence. So you know there's 10 carbon must have some heteroatoms using this carbon. So that's why we calculate that. So that's a way, one way to, at the low resolution, you can do. As I also mentioned, if you have the n plus 2 signal, if you have chlorine, then you will see a 30% intensity of n plus 2. You have bromine, you have 1 to 1 ratio n plus 2. Then if you have sulfur, will have around almost 5% of n plus 2. And silica, you have 3.6% of n plus 2. So this is help you to determine the elements formula. So nowadays, most popular method used is for the high resolution to determine the molecular formulas. So the principle is like we defined that molecular mass carbon 12 is exactly 12 mass unit, and right? So all other elements is compared with carbon 12 to get a mass unit. However, when this nuclear fused, then you have some mass deficiency. So for other elements, they are not exactly whole number of that mass. So like hydrogen is 1.00, I do not remember, 1.078 something. So for oxygen is 15.99, 6 or something like that. So you see a little bit off the full number. So if you see for molecular mass, so molecular mass 98.0372, this is or you say a theoretical measured number. So if you calculate a formula for this 98 mass, so all this formula fits to the 98, right? But if you see the decimal place, they are all different. So you see this 372, then it's only like match with this one, 368. So that's we see. Generally, we accept the accuracy value 5 ppm. So for less than 5 ppm, only this formula is possible to make that. So that's really, if you can measure your mass very accurate, like to 4 decimal place, then you can use this accurate mass to judge which one. Okay, for larger resolution, no way since all of them are accurate, right? But for high resolution, you do everything. So these high resolutions, especially for molecule is not that large, then probably most time you get only one result. So, but when the molecule is very large, then you probably have increased even with that 4 decimal for within 5 ppm, you may still get a number several that fits the formula fits to that accurate mass. Then you need to use additional other information to make a judgment of which formula it should be your molecule. Okay. So that here you see one example why we need the high resolution mass spectrum. So that's the only high resolution can do. Okay. So that's a TOF machine can do Orbitrap and SER mass can do this. And traditionally double focus can do high resolution. Okay, so this table is give you this accurate isotopic mass. So when you calculate a high resolution mass, use this mass. Again, do not use period tag. Again, remember, okay? So, and also the abundance, each isotopic abundance is there. So when we calculated the molecular ion, the molecular mass, we always use the most abundance isotope to do the calculation. So for carbon, use carbon 12. For nitrogen, you use nitrogen 14, oxygen 16. And not always every element's lowest mass is the most abundant. So what is reality? So like the boron, so the large one, 11, is more abundant. So boron 10 is like one less is like 25%. So it's, do not think always, I just always use the lowest mass of the isotope. Okay, use the most abundant. So for chlorine, you use chlorine 35. So chlorine 37 is 32%. Right? For bromine, you have bromine 79 is 100, bromine 81 is 98%. So you use bromine 79. So here also shows you some example of this high resolution and low resolution. Here you see if the resolution is 1,000, so you see a peak like this one. So when the resolution is 20,000, you see you have two of these peaks. So the difference is in that 4 decimal place. So in fact, these are two numbers. So that have different place. But if you have a low resolution, you cannot see. So, and here shows a protein mass spectrum. So each of these peak, like this one, since it's a multiple peak, if you expand it, I think this one probably, this one expand, we expand this one, you will see a peak like this one. So the difference is very small. So here says this Z is 15, so it's kind of 15 charge. So 15 charge, think about the isotope. So carbon 13 isotope difference mass is 1, right? So that 1 different, then now you have 15 charge, then divide by 15. So then the difference will be around 0.06, right? So then each peak difference is 0.06. So that's, we said the low resolution mass generally you can separate 22.1. So this is already below the low resolution mass. So if you have a low resolution, you just have a big height. You cannot see all this isotopic peak. Okay. So that's why when you do the large molecular protein, you always need a high resolution. So almost biology still always use high resolution. But for small molecular, most time we use low resolution. So we always have 1 charge. You hardly have 2 charge. So this slide talk about the heteroatoms in your molecule. So we already mentioned it. So use the isotopic peak intensity, bromine, chlorine, sulfur, and Zika. So you can use that N+2. So this spectrum also, you see the spectrum, the molecule have 1 chlorine. So you see the N+2, 128, 130. So there's N+2, and N+2 is around 30%. So basically, you can see it around 30% when you work on it. We do not really measure exactly. It's 30.1 or 30.2. And here, from this one, you cannot just tell if you have a nitrogen. So it's nitrogen N+1 just 0.07, and you have carbon have a stronger N+1, so that will not help if you have nitrogen or not, just from here. Okay. But if you have a high resolution mass, sure you can get a very conformed Okay, so this is another example. If you have this molecule have 3 chlorines. So 3 chlorines is 1 chlorine you have a little bit 32% of possibility of this chlorine 37. So if you have 3, then the n plus 2 almost 100%, right? So that's why you see n plus 2 almost equal. And since you have 3 chlorine, you can have 2 chlorine 37. So you have n plus 4, and you get all 3 to be 37, and you have n plus 6. So this kind of isotope ratio can help you to determine if you have multiple of these isotope, the specific elements isotope. So this one is shows you if you have like 1 chlorine, 2 chlorine, 3, 2, 5 or 6 chlorine, so that isotopic peak that pattern for bromine, and have bromine and chlorine, how it looks like. So do not think like, okay, I have 3 chlorine, you see, n plus 2 is almost 100%. Then for the bromine, you have 1 bromine, n plus 2 also 100. So that one and this one, the difference you have n plus 4. So that indicate it's not a bromine, present 3 chlorine. So that pattern. So this table is give you more of these isotopic elements. So you have here you have n plus 2 and n plus 1, and you also have n minus 1 metals, so like lithium lithium 6. That's about this. So you see the lithium 7 is 100%, and lithium 6 is 8%. So it looks like M minus 1. So everybody understand isotopic? Next, and also how do you apply this isotopic intensity? Okay, so apply this isotopic intensity for this elements determination and formula determination. Okay, that's a part for all this scale we are just talking about. When you see a peak, what's a peak isotopic relationship. So this isotopic does not only apply to molecular, to every peak. Okay. So that's why for each of the peak you will see an isotopic class. Okay. So now we move to the fragmentation. So for fragmentation, as we said, it's like you lose one proton molecule is not stable, then one bond will since for organic molecule you have all covalent bond, so the covalent bond will be cleavage, so to forming a fragment. So if a fragment like positive charge ion fragment is stable enough to reach the detector, then you can detect it. So here says from this ionization to the mass detector is 10 power to 95 seconds. So that's from the ion generation to hit the detector is this time. So if an ion can survive this long time, you can detect it. So if the ion cannot survive that long, then it becomes a fragment. So then you will detect the fragment. Okay. So that's why for mass spectrum, you see the molecular ion may not be the very strong, since majority of them is fragmented before it reaches the detector, right? So for this fragmented in mechanism in that mass spectrum, so it's, generally it will be a unimolecular reaction. So basically, since in the mass spectrum, first thing you have a vacuum, right? So you only have one type of molecule. So second one, since the concentration is very low, so two molecules hardly have chance to combination each other. So the reaction always just one molecule. So generally you have a bond breaking. The bond breaking will be evenly breaking. Evenly breaking, if you bond two electrons, or if one electron goes to this side, another electron goes to another atoms. So evenly break. Of course, if you do not have two electrons, since you already knocked out one electron, so then the way is just one electron go to one atom, so another atom will have a positive charge. So definitely you have one free radical charge. So since as we said, an NMR only can measure the ions. So and also this ion has to be stable enough to reach the detector. So basically this what you see the fragment, in fact, is especially the intensity of the signal is just how stable the ion. So if you have the most stable ion, that will be forming a base peak. And also remember this is relative, so you follow all your fragmentation. So which one is the most stable and will form the base peak. So it's less stable than will be the low abundance fragmentation. So that's basically that mass spectrum. And also since when you're forming the fragment, you not only have the ion, you also have a free radical. So, but however, since mass spectrum only seeing this ion, so a stable free radical is not important. Since although it is stable, you cannot see it. Right, mass spectrum does not show it, so you just focus on stable So generally, for the general mechanism of this fragmentation, so first one we're talking about is one bond sigma cleavage. So basically, it's a second bond. So second bond cleavage. So that if you have a carbon-carbon bond, so it's carbon-carbon bond, so it's carbon bond cleavage. So since it's already a charged ion, so this should be pass. So so this one you see, so this bond only have, it's not one pair of electrons, one electron. So the one electron goes to the carbon, so then leave another carbon, a positive charge, and this carbon free radical. Okay. So if you have carbon and heteroatoms, so you cleavage, so since the heteroatoms are always more electron active, so which means it always multi-electron. So when cleavage mostly this electron go with these heteroatoms. So then you have this carbon positive charge. So that's sigma cleavage. And for this carbon heteroatom bond, so you can have an alpha cleavage, which is the next alpha bond. So you can open this bond broken, say one electron transfer to this bond, so you form in here like this one, free radical. All these when you have this one, this bond, if it is here, the things here you see this charge and free radical is located on the hetero atoms. So if this charge and this free radical is in carbon and hetero, so you can broken from here, then form a double bond here, so you have this and if you have a double bond hetero pattern, so you can broken from here to form this kind of mechanism. So most time you have like one bond cleavage. Since two bond cleavage, you break two bond, always need more energy. So you have to have a very special mechanism. So, but generally, if you have two bond cleavage, that's a good thing for your structure elucidation. That special mechanism remind you that special structure functionality. So help you to determine the structure. So for two bond cleavage, so the first one is an elimination reaction. So like everybody knows, if you have an alcohol, so you can have a hydroxy group in a molecule generally can have a dehydrate, right? So like here, if this is a hydroxy group, so you can dehydrate to lose the water, so form the bond that way. Of course, if this is a halogen, you can lose hydrogen and halogen, like hydrogen chloride, hydrogen bromide, so you can lose it. That's a double bond elimination reaction. Okay. So for other two bond cleavage, there are one is called retro dialdehyde reaction. So the other reaction, you have a die-in. So conjugated die-in react with in that will add up to forming a six-member ring and generate a new double. So that's very often used to synthesis of six-member ring for organic chemistry. So for this mass spectrum, if you have a six-member ring with a double bond, you can go reverse the diazide reaction. So you get a die-in and in that case. So because it's special neutral diazide reaction, so this cleavage of two bond do happen. So when you see a structure have this hexene diazide reaction, that's you looking forward for this verification. And another two bond sigma cleavage is called a McLaughlin rearrangement. So that one you need to have a double bond. So this double bond could be just a carbon-carbon double bond, carbon-nitrogen, carbon-oxygen double bond. So when you have a gamma proton, gamma carbon have a proton, so you see these protons are very close to this one, forming a six-member ring, right? So then this proton, since it's six-member ring are close and low energy, so that proton can transform. So that proton transform, then connect to here, then this double bond open, forming a single bond with a hydrogen, and this bond, when you open one electron will move to here, and you broken this bond, this one electron will form a bond with the electron move from here, bond, so it's like here, bond. So here, since you broken here, one electron go to here, forming bond, and one electron come here, is broken, one electron, so they're forming a double bond here. So that's McLaughlin rearrangement. So when your molecule have a carbonyl group, have a alkene, always think about this Lafayette. So another thing is when you see when we see the mass spectrum, we see a sigma cleavage. Sigma cleavage is like separating in half, right? So you want to see the fragment if without nitrogen. So the molecule is even, and you cut in half, it's always odd. So for most of the spectrum, if you see the molecular eye even and all fragmented, mostly like odd number. So that odd number remind you that's one bond cleavage. So when you clean with two bonds, then you will generate an even number of fragments. So that's a way when you see, okay, I have molecular ion even. Then I see a fragment significant intensity have an even number. Immediately remind you that's a double bond cleavage. So that double bond cleavage only 3 mechanisms. Very special. Remind you some special functionality. So you may quickly identify what class of this one. Couple here, so that kind of thing. So this is very important. So you always want happy to see some even number of fragments. So So for this, well, we see this mechanism of fragmentation, 1 bond, 2 bond, sigma cleavage. So as we said, we detect the ion, the key thing is the stability of it. So how do we know the ion stability? So one thing is like, for these alkanes, you can see there's a tertiary alkane stability will be larger than secondary, larger than primary, larger than major. So for you have a structure, if you have a sigma cleavage, you will see if there's a, you can form a tertiary cation, that one will be stable. So that will be a strong signal. So if you just lose one methyl group, the methyl group does not hold that charge very well. So tertiary, basically you have 3 carbon connected. So when you form a carbon cation, so that 3 bond with this carbon hydrogen or carbon bond, each bond have a pair of electron, then the pair of electron will share with your positive charge. So that way stabilize the cation. So for the methyl group, you only have a carbon hydrogen bond. So carbon hydrogen bond basically is less than carbon. So that's less than the secondary. So that's why that the tertiary is more stable than secondary than primary. Then of course you know the benzene ring have a big pi electron. So they have a lot of electron. So you lose one, not a big deal. So still pretty stable. So then the double bond ally also the double bond have 1 pair electron. So the 1 pair electron will share with the cation. So they reduce that deficiency of that electron. So you get stable. So basically you apply this general chemistry principle to determine which ion is more stable. Okay. So that's the general mechanism of this fragmentation. So now we move to this fragmentation pattern of each class of molecule. So maybe you have a tea break, then come back for.
We have 20 minutes until tea. I don't know if it's out yet.
Okay, 20 minutes left, so keep going. So at this time, I will talk about all these different class of molecules and their specific fragmentation pattern. So since you knowing this fragmentation pattern, when you analyze spectrum, it's the worst. So we do not know the structure. You from that spectrum, you try to find this kind of pattern. Then you say, okay, this probably have this kind of functionality. So that's it. Okay. So the first class is alkane. Alkane basically just saturated carbon and hydrogen. Right? So you only have carbon sigma bond, carbon hydrogen sigma bond. So think about this molecule does not have any special function. You only have a sigma bond. So there's only one mechanism cleavage that's sigma bond, right? So it's carbon-carbon bond cleavage. So, but as we said, it's like if you have this tertiary carbon is more stable than secondary than primary. So think about the molecular cleavage will cleavage to generate a tertiary carbon cation. more stable than the secondary. So basically, if your molecular can generate a tertiary carbon, so that will be a strong PBOC. So that's like if you have an isobutane, so you lose one method is forming an isopropyl. So isopropyl is a secondary cation, so it's stable. Then of course, these molecules do not have other choice. But if you have the longer chain, so if you say long chain, you continue long chain, so you are broken here to form the isopropyl, the most strongest. So you broken other bond will be less. And also here says, so you see the positive charge you are more stable at this secondary carbon than the primary vessel. So here says block out, it's not called a block out, just like this intensity will be much stronger. Okay, since this stability is much more, so even this form, the majority will not survive to but for the chemical reaction mechanism, so mostly will be this one, or be this way, or be this way. So here are some sample example of this alkanes. So the first one is the linear alkane. So generally for alkane, if the molecule is small, you will see a pretty good molecular ion. So here, this one you have molecular ion 86. Okay, when this becomes very large, very long, the molecular ion goes down, and very long you will be seen. And also, the molecular ion will be strong when it's linear with a branch. So we said branch, you have tertiary carbon. The tertiary carbon that cation is stable, which means that fragmentation is easy happen. So fragmentation easy happen, then your molecular ion will be less intensity. So that you compare these two. So this molecular ion is much weaker than since you have a branch. So for this one, since you all have sigma bonds, so just cutting whatever sigma bond. But generally, you are cutting a large part. So like if you cut from here, so you lose a large part. That ion fragmented will be the more stronger one. Okay. Like here, 86 to 57, what's the mass difference? What's the mass difference? 86 to 57. What's the neutral loss? Yeah, that's correct, 29. So 29. So 29 corresponding to like CH, this is a CH3, CH3 is 15, right? 12 plus 3, 16, 15. So here is a CH2, that's 14. So 15 plus 14, 29. So you just basically, you cleavage this bond, so you keep the ion in this large piece, that's 57. Of course, if you keep the ion in this 29, you do see 29. So that's a cleavage. And here you can lose, this difference is 15. So 15, you just lose one, this methyl group. So either side does not matter. So that's lose 15, lose methyl group, right? So if you split from the middle, that will be 43. So the ion does not matter either side. Okay. So for this one, you see, so for here, you see this loser methyl group, 15, is much stronger than this one. So why? Can somebody tell me why this 71 is much stronger than this one? So think about which method it's loose. You have 1, 2, 3 methyl group, right? You can group here, here, or here. You all get is N minus 15, right? So for here, do you think which methyl group will be preferred to use? This one?
No.
Yes. Since think about it, if you clip it here, this is a secondary carbon, right? Secondary carbon cation is more stable than if you clip it here, so you have a primary carbon cation. So if you clip here, this one is not as stable as you clip here, this positive charge. Since think about this carbon, you have 2 carbon-carbon bond. So each carbon bond have 1 pair of electron. So this is positive, then this 1 pair of electron can share with that positive charge. This pair of electron also share with the positive charge. So kind of reduce that carbon lack of electron, right? So for this one, you only have 1 pair of electron to share. So then this carbon, positive carbon is more like a charge. So this charge will be kind of distributed through this share. So that's why this is more stable. So you use this one. So this is stronger since it's stable. So you see the 71 mostly is like because moves off this one, not this one. Okay. Of course, you can have some contribution from moves off this one. Still percentage. So, and also you see this 43. So what's a 43? So for 43, here you only have 1 choice to pick from here. So, but the 43 will be this part or this part. Since when you clip it from here, this part is 43, this part also, and over here also 43. So what do you think is 43 is more like this part or like this one? The same principle can apply. Yeah, the same principle we can apply since it's like if we keep the positive charge here, so you see you have a secondary carbon cation. So it's stable if you put the charge here, right? So the 43 we said is an isopropyl, not propyl. Okay. So that's why you see the 43 become base peak. That 43 over here is not. That's because this 43 is not stable. So this so you see these 2 molecules have exactly molecular formula isomers, but from this fragmentation, in fact, you can distinguish them. Okay. So the mass spectra looks different from this one. You can determine if you. I do not give you structure. Just tell you both of them are 1, 2, 3. Both of them are hexagon, right? So which is which? You can provide a structure. So that really because it's stronger 43, you know that have a stable part. So that's a way you determine the structure of your mass spectrum. So another example, so for this still the alkane, so now you have a tertiary quaternary carbon here. So we said tertiary carbon cation is the most stable, right? So of course, when you see this one, you immediately think of broken here forming the stable R. So this becomes very strong and dominant for this structure, for this spectrum, right? And you see the molecular ion becoming even long because easy broken to forming a stable ion. Okay, and this becomes so strong, dominant, so other one is much smaller. So basically here, summary of this alkanes fragmentation. Basically, just remember, if you have a branch breaking from the branch, okay, and always lose the large branch. So when you have branch, you have meso group. Mostly the strongest peak is you lose the large branch rather than lose the meso group. Okay. So basically, that's it. So when you have 43 and 57, immediately from there, you know you have either the tertiary butane or isopropyl group in your structure. So you see that, you write your structure, immediately write isopropyl, C43, and if you see 57, you write tertiary butane. So that you have a functional group so building the structure. So that's a linear alkane. So for cycloalkanes, so if you have like the alkane, but you have a ring. So for a ring, if you want to form a fragment, obviously you have to broken two bonds, right? Broken one bond, you only open the ring, but still not a fragment. The mass does not change. So for this hexane ring, you have something similar, a little bit like the Richard Diels Ires reaction. So like the broken here, form the diene, form an ene, and also this whole thing share with this electron. So that's the 56, that's a strong signal, since you have all this kind of congregation that to share that charge stepwise. So that's cyclol. And of course, because this is a cyclol, you have to break in two bonds to fragment. So that's why you see this molecular ion is much stronger than that previous linear one, right? So you have to break two bonds. So this molecular ion almost the same as the base peak. So that's about the alkane. So now, any question about alkane fragmentation? So now let's move to the alkene. So alkene basically is a molecule that has one double bond. So basically the difference with alkene just that won't have one double bond. So basically the alkene will have all these alkanes fragmentation in addition to something specific for the double bond. Okay. So since you have a double bond, generally this molecule can easily more stabilize right? So for this reason, generally alkene, the molecular ion intensity should be better than alkane. Okay. For alkene, what kind of fragmentation can you think specifically? Since it's just for the double bond. We mentioned like a two-bond cleavage mechanism for double bond, which called molecular rearrangement. So when you have a double bond, then if you have a gamma proton, then forming a six-member ring, so that hydrogen can be transformed to have two-bond cleavage. So that's one thing specific different from alkane. So of course, since your alkene have two mass units less than alkane, so for alkane, mostly you have 43, 57, 71, that series of peak, 29, 43 there. So for alkene, since you have two mass less, so you have 41, 55, 69, that series of peak difference. And if you still have a terminal alkene, since this beta bond cleavage, then this double bond can stabilize this carbon cation like this one. So you go from here, so the cation can be stabilized by the double bond. So it's sharing this pair of electrons. So you will see this piece of fragmentation. very strong. See an example, so here you have this two propane. So you see the molecular ion, this is pretty strong, right? Remember that hexane, your molecular ion is just like that 20%, 10%. Now this is like 40 to 50%. So because the step bond can stabilize the ion, so that's so then you have this 55 just different with 15. So that's lose one of its methyl group. So basically, if you lose this methyl group, since this step bond will share with share the electron to stabilize that cation, so that becomes very strong, most stable. So that's a major fabrication. And let's see another one. So this one still, this is a little bit longer hexane. So, okay, this is a hexane, exactly with previous example of hexane. So you see the intensity molecular ion. So of course you always have a loose methyl group. So 15 difference. Then here, since the double bond, if you broken from the beta position, so again stabilize, you have the 41. This is very strong. And in addition, you see the 41, you see a 42. So this 42 is not an isotopic peak. Since you see this intensity, since for this molecule you only have 6 carbon. So if it is n plus 1, it's only about 6% of n plus 1. So if it is isotopic, it's only will have very small 6%. So this is like 80% of that interpigment. Surely it's not isotopic. So this must be have a special mechanism, 42. So what's 42 reminding you guys? You have to do the 2 bond to make a union. So for double bond, what's the mechanism for 2 bonds? Yeah, the arrangement, McLafferty rearrangement. So basically, you see here you do have a gamma carbon, and if you write another way, you can write it. So you can write like six member ring this one. So this proton is close to the I think 6 member ring. That's okay, thank you. So you can write the transform, so that clearly. So that way, this one you transfer one proton to here, so the 41 become 42. So that's why you have a stronger 42. So that's one always watch on with evening level. So that always remind you of some special structure. So here, this is a comparison of this alkane and alkene. So first you see the molecular ion. So alkene, the same is stronger than this one.